The next nucleophilic addition reaction that we will talk about is reactions of aldehydes and ketones with phosphonium ylides to produce alkenes. Okay, this reaction is well known as the Wittig reaction, which is a Nobel Prize winning reaction. It's a remarkable reaction because it allows the transformation of aldehydes and ketones into alkenes with additional carbons by reactions of aldehydes and ketones with phosphonium ylides. So it is actually the phosphonium ylide that act as nucleophiles in the Wittig reaction on the aldehydes and the ketones. In other words, phosphonium ylides do nucleophilic addition reactions on aldehydes and ketones to produce alkenes in what's called the Wittig reaction. Let's draw a general representation or scheme of the Wittig reaction in order to understand what's going on. So if we take, for example, a ketone of this type, that's a general structure for ketones. And if we react the ketone with this interesting intermediate, that is called an ylide. It's also a phosphonium ylide because there is phosphorus here, and this phosphorus is positively charged. This is like a carbanion, but the carbanion is next to a positively charged phosphorus. This is called an ylide. An ylide, by definition, or scientifically, or strictly defined as a species where there are opposite charges adjacent to each other. This is called a phosphonium ylide. When a phosphonium ylide reacts with an aldehyde or a ketone, an alkene is actually produced in what's well known as the Wittig reaction. So this is the product. Therefore, so that's the alkene product plus a byproduct, which we will talk about when we discuss the mechanism, triphenylphosphine oxide. If you look at the phosphonium ylide has opposite charges. So there is a positive charge on phosphorus. There is a negative charge on carbon. We can actually draw a resonance form or resonance structure for the phosphonium ylide by taking that lone pair now from carbon and making a double bond between carbon and phosphorus. And if we do that, we get another resonance form. And this resonance form is neutral actually. This form or this intermediate or this structure is not called an ylide strictly speaking. It is called a phosphorane. So this is a phosphorane. So that's a phosphorane and that's an ylide, and the ylide and the phosphorane are actually resonance forms with each other. Mechanistically, we can use either of them to illustrate the nucleophilic addition reaction in this case. So we can use the carbanion to make it attack the aldehyde or the ketone in nucleophilic additions, or we can draw an arrow from the middle of carbon, phosphorus, double bond. It doesn't really matter. So what we can do now is we can take the ylide. Let's use the ylide. So that's the phosphonium ylide, which acts as a nucleophile. The nucleophile then, the phosphonium ylide, a carbanion if you like, also attacks the aldehyde or the ketone, a nucleophilic addition step of that type. So if we get that, if we do that, we get something like this as an intermediate. So that's the intermediate that's produced when the phosphonium halide attacks that general ketone. If you look at this intermediate, it's still charged. It still has opposite charges. This intermediate is actually called betaine. So this is a betaine intermediate which is produced as a result of the nucleophilic addition of a phosphonium halide on aldehydes or ketones. What the betaine can do now, it can actually cyclize. So that negatively charged oxygen can attack the positively charged phosphorus like that, as indicated by Cayley arrow. So we can make a bond between oxygen and phosphorus like that. So this the betaine intermediate will therefore cyclize to get another intermediate like that. So this is another intermediate. It can be viewed as a cyclized betaine. Now this is not called betaine. It's actually called oxaphosphatane. Oxaphosphatane. So the betaine cyclizes to the oxaphosphatane. Now this oxaphosphatane will collapse basically. It will collapse to give the final alkene and triphenyl phosphine oxide product. We can indicate the electron movement which would show how the product is formed by using such Cayley arrows. You break that phosphorus carbon bond, so you take the arrow from the middle of that phosphorus carbon bond. We make a double bond here. This carbon oxygen bond must break simultaneously because carbon cannot exceed the octet. It's in period 2. So this carbon oxygen double bond will now break, and it makes an oxygen phosphorus double bond at the same time. This is a concerted type mechanism, if you like. Formation of a carbon-carbon double bond, formation or breakage of this carbon-oxygen single bond, formation of an oxygen phosphorus double bond, and obviously breakage of that phosphorus carbon single bond. Now this releases or gives rise to the alkene product, and at the same time a double bond between oxygen and phosphorus is formed to give triphenyl phosphine oxide, which is a precipitate. This is actually a precipitate. It's a white solid, which you could see even clearly if you do this reaction in the lab. Now formation of that triphenyl phosphine oxide is thermodynamically favored. The oxygen phosphorus double bond is very strong. The bond energy is very high. You're talking about 575 kilojoule per mole. That bond is very, very strong thermodynamically. So therefore collapse, if you like, of this oxaphosphatane to give the final alkene product, and of course the thermodynamically very stable triphenyl phosphine is very thermodynamically allowed or thermodynamically driven. So we can write that down, that this byproduct is thermodynamically stable. So it's like a driving force for the Wittig reaction, that is the formation of triphenyl phosphine oxide, because it contains a double bond between phosphorus and oxygen. So this is like the driving force again, or the thermodynamic push for the Wittig reaction. To take an overview of this reaction, the Wittig reaction, aldehydes and ketones react with phosphonium halides in nucleophilic addition reaction to give the alkene product, and triphenyl phosphine oxide, which is thermodynamically stable. That's due to the incredible strength or incredible thermodynamic strength of the phosphorus oxygen double bond.